So, so, all right, everyone. Thanks a lot for being here. And today we are very happy to have Shawn here to give the talk. And Shawn is now a PhD student at the University of Chicago. He obtained his master and bachelor degree at the University of Chicago too. And his research focused on the security and privacy of machine learning systems, exploring the vulnerability of machine learning systems, and protecting users from malicious use of machine learning systems. So his work has been covered by many media outlets such as New York Times, NBC News, and so on. So today he's going to talk about the security beyond defenses, protecting DNN system via forensics and recovery. Thank you so much, Shawn, and the floor is yours. Please go ahead.
All right, thanks, for the intro and everybody for coming here. All right, so today I'm going to talk a little bit about some of our recent research on kind of looking beyond just defenses for ML security and robustness. All right, so to start this talk, let's forget about ML, forget about digital security for a second. Let's imagine we're a bank, right? We're a financial institute, and the goal of our security team is to protect money from robbers, right? Very simple. Right? Then we say, well, that's pretty easy to do. Existing banks all does this already. We just hire a couple of security people. We hire or we buy a safe, and these two measures itself will be able to stop most of average robbers, you and me, who are not professionals, to take money from the bank. Right? So, but this is probably not enough for more professional robbers, right? Stronger attackers who has more experience, more resources, they can probably break these defenses. Right? So you can say, well, then that's fine. We can hire more security guard. We can put a bigger safe. But is this enough, right? Will any of these strong defenses be enough to stop all possible robbers in the world? Right? I think the answer is probably no, because we have all seen in the news, we have all seen movies based on real events, that there are very strong, very persistent attackers out there. No matter how strong your defense is, it's very likely that they will break your defense, right? They can spend 10 years digging a tunnel. They can spend millions of dollars. It can be in nation states. So it seems that from this example, it seems that regardless how strong you build your defense, there seems to be always a stronger attacker that can potentially break your defense, right? And sometimes if we take cost into consideration, your local bank is not going to spend millions of dollars to secure their vault, for example. And so this exact kind of back and forth or this exact scenario of attack and defense, we can observe this in kind of the ML security space that we're working in. Right, let's take adversarial example, for instance. At the very beginning, we have fairly weak attacks, FGSM, Deepful, and we build defenses to stop them. Pretty effective. But then we all know these defenses are broken by later stronger attacks. And we build a little bit more complicated defenses, and then also broken by stronger attack later on. And they just keep going, more attacks, more defense are proposed, but all quickly broken by kind of later attacks. So this keep going until today. And I think all of us probably agree that for a realistic system out there, there really doesn't exist kind of a known defense against white box adversarial example, right? Under the strict white box setting. You can say, well, there are, adversarial training, there are certified robustness, but they have, pretty significant caveats, right? They don't really generalize well to large models, and the bound is fairly limited for, real world users. Okay. So it seems that this back and forth has been going on for, a decade for now, and we don't really see, a way out here, right? You seem that we have to keep playing this cat and mouse game back and forth from attacker and defender. And many of us, including people in our group, has been thinking, well, are we stuck, right? Are we making any forward progress along this kind of making system in real world robust, right? The same, the defenses we propose today are also quickly broken by stronger attack, just like 5 or 10 years ago. And it almost seems that a perfect defense is nearly not possible, right? This is not just adversarial perturbation. They're also for poison attacks, for membership inferencing. it seems that defense is very hard to do, especially against a very powerful attacks. Right, there seems to be, the building asymmetry between attack and defense. Right, attack are just a little bit easy to do because it comes after defense. Right, the attacker can analyze exactly how defense is doing and try to circumvent it. So for those of us who working on robustness, what is there to do? Right, we can of course keep working on defense. That is a very important space. But some of stuff we're thinking is, well, how do we break the cycle and really just quickly improve the situation for real systems, right? Rather than waiting for certified robustness to catch up or waiting on speeding up robust training. So our approach, we took a look, is expanding our threat model. I'll explain in a second what does this mean. But we try to look beyond defenses and take a look at in the real world, what is exact the threat model that are faced by real world deployment system. Right, let's go back to our example of the bank. Right, we have defenses. We call this attack prevention. Right, they're trying to, whether it's a vault, whether it's a security guard, they're all trying to prevent attacks. And in real world, prevention fails all the time. Right, so I think in the U.S. there are around 4,000. There are 4,000 bank robbery or successful bank robbery even every year today. Right, that means bank robbers are successfully break all the prevention people had put up, get the money out. But that is okay, right? Especially in today's world, the bank robbery probably is not the #1 concern for most banks. And the reason, well, part of the reason is that there are other mechanisms that can help attack prevention to improve the robustness. But one big part is something called post-attack solution. Right? Post-attack solution happens right after a success attack. And in the bank robbery case, right, 60% of the bank robbers are caught, right? The money mostly are recovered to the bank, but really there isn't that much of a damage to the bank, even though the attack is 100% successful. So what does this post-attack solution mean, right? In this case, I think we all know there could be, security camera, there could be fingerprint analysis after the attack. So the goal is to basically catch the attacker and put them in jail. Okay. And so I want to point out that even all of these are security systems, but security cameras or fingerprint analysis are not attack prevention, right? They are called attack attribution. They're not, part of the defense. And of course, this post-attack solution is not a new space. This is well explored in kind of computer security. I think for people familiar with malware, there are malware attribution. There's malware fingerprinting. Is how do you fingerprint an existing malware so to detect it more easily in the real world. And there's also provenance tracking of APT, intrusion detection, and also there's IP-based traceback for DOS attack. Right, once DOS attack happens, how do you find the true source of IP of the attacker who was sending all these requests try to overload your server? So again, these are not defenses, but they are a very important part of the security system. And the goal of post-attack analysis really is to answer one or some of these questions. Is taking a look at a successful attack incident or a successful intrusion. We take a look at why this attack happens, or who are the attackers, and also, of course, how to prevent similar attacks in the future. So you can imagine answering any one of or group of these questions will really help to increase the robustness of existing systems. So many of my work has been focused on applying post-attack analysis for machine learning security. And so today I'm going to talk mostly about 2 papers on this topic. The first one was that Unix that looked at digital forensics for data poisoning attack. And the second one, CCS, was about recovery, which I'll explain in the second half of this talk. All right, so let's talk about forensics. So forensics, I think most of us know, kind of what it means, but more clearly defined in the digital case is that you have attacker, you have your defense, you have your system. Attacker has already successfully penetrated your defense, right? Break your defense, has caused a misclassification on your deep learning system, say, it caused their malware to avoid your malware detector, right? Or their stop sign was able to crash a Tesla car. So after these already happened, Forensic happens post-attack, right? It looks at, well, taking a look at this attack incident and look at any traces left by this attacker. And then the goal of forensics is to identify what is the attacker's identity. And in this case, or in digital case in general, identity doesn't mean their physical identity. It could mean their IP address, their location, or their account number. And once we have some of this information, we can prosecute or mitigate the source of this attack by, say, banning these IP address, close account. And in some rare cases, if we have enough resource or information, we can even put attacker to court, right? Use the legal system to really prosecute the attacker to stop them. And perhaps more importantly, the second benefit of forensics is that it can serve as a deterrent. A deterrent means, the fact that I know I have a very high chance of being get caught, even if my attack is successful, this alone will stop me or make me double think before I try to attack an existing system. So these are some benefits. Of course, there are more benefits for forensics that we'll explore very well in the traditional kind of computer security literature. But in today's talk, I'm going to talk about how we can apply some digital forensics concept for machine learning-based attacks. I will look at data poisoning more specifically. A quick refresher on data poisoning attack. Right? Very simple. We have some benign data. You try to train a model. There is a malicious data provider or malicious data labeler who contribute these malicious data. And you don't know which are the malicious data, so you train a model, and this model has a backdoor inside. And at deployment time, this attacker can use this backdoor to trigger target misclassification. I say the stop sign will get misclassified at the speed limit. So the goal of forensics is to take this misclassification, which we call a misclassification event. And the goal is to trace back to the source or to the cause. Right? In this case, the cause of a poison attack, of course, is the poisoning data that are injected into the system. And say we can successfully do this trace back, then we can also identify who are, say, the malicious data provider who send us all the malicious data. And at a minimum, we can stop using this data provider in the future, right, to stop future attacks. If we have sufficient information, we can even take further steps to prosecute these malicious data labelers. All right, so this is how forensics work. I just want to quickly just reemphasize that this is pretty different from defense, right? Defense is try to stop this misclassification from happening from the first place. But this is, your defense already failed. How do you at least find out who is person is trying to attack you? All right, so let's take a look at how we do this, right? It may seem pretty simple, right? All we need to do is to go from this misclassification to the model parameters that are responsible for this misclassification, and then to the training data set that are responsible for causing these parameters. But realistically, this is pretty hard to do, mostly because, as we know, deep neural networks are very hard to interpret, right? It's very hard for us to reason how does the model weight exactly impact a classification results, and also how does training data impacts the model weights. And secondly, there's another challenge is that poisoning oftentimes a group effect, right? That means individual poison data may not be successfully cause this whole misclassification by itself. Mostly it should be a group of them working together, or a group of poison data working together to cause this misclassification. Right? That really means you have to identify a sufficient subset of poison data before you can observe any signal, any changes in the misclassification. All right, so to address these two challenges, we propose our solution, which is basically a trick on kind of clustering and pruning. Right? The idea is to cluster training data into the groups, and then we'll iteratively remove benign data from the entire training data set until we're only left with poison data. All right, let me show you what this means. So given all these, say, training data set, we don't know which are poison, which are benign. What we do is we first cluster these data into an embedding space. So I will talk about exactly how we're doing this clustering in a second. But once you cluster these data, we do a binary k-mean or two-mean clustering to separate the data into two clusters. And then we use the second component of our system, which is to identify the benign clusters, which of course I'll talk in a second as well. So we can identify that the cluster on the right is only benign data. And then we basically filter this cluster out and continue the clustering process on the rest of the input or rest of the training data. And in this way, we can know that the top part is benign and then keep going until we're left with both clusters that are malicious. So we output the rest of the data as malicious. All right, so this is how it works at a very high level. But let's talk about the two components that can make this possible, right? The first is data clustering, and the second is how do we identify benign clusters from clusters that contain poison data. So data clustering first, right? Clustering is this idea that we move the training data into similar embedding space where similar types of data are close with each other. So there are quite a few kind of clustering heuristic or techniques in the literature, right? You can cluster based on feature space activation. You can cluster based on gradient. So we tried many of these, and many of them does not work really well or does not generalize to all types of attack. So we kind of propose our own trick. We call it some signal that summarize how a training data point impact the model parameters, right? It's based on a gradient calculation. I'm not going to go into the details of how exactly we're calculating this, but it's simply to take a look at model gradient, but with respect to a different label to see how does changing this single input will impact the model parameters. And then we use that gradient as an embedding space. And more in detail, of course, is in the paper. I'm also happy to answer questions about this later in the Q&A. And the second component of our system is to, how do we identify benign clusters from poison clusters? So let's say we have, cluster A and B, right? A contains some poison data, B does not. And we don't know this. We want to see, who has the poison data. Right? So we do this using counterfactual reasoning. But the idea is, let's say we take B, and we want to label B first. Okay, so we're going to take B, and we're going to remove B from the entire training data set and train a new model. We call this model A, only on cluster A. Okay. And now, since the poison data is still in cluster A, the new model will still have the exact same backdoor or exact same bias as the original model. Right? So the misclassification will still be successful in this new model. And remember, we do have the misclassification from the attack time, so we can use this to replay this on the new model A to observe whether it's successful or not. And then we can take a look at cluster A. If you remove cluster A and only train a new model on cluster B, then the attack is no longer successful, right? Because cluster B only contains benign data. You know for sure that cluster B only contains benign data, cluster A contains poison and potentially other benign data. And so this is how we identify benign data. And you may have already noticed that this is very expensive to do, right? You have to train a lot of different models based on how many iterations of the pruning or clustering you're going to do. And this is very expensive. I think if you do this, it will take around a month to perform a forensic run for the ImageNet data set. So we try to speed this up by approximate the training on a new model on the rest of the data to unlearn the current cluster from the original model. Okay? Unlearning is this idea where you just simply remove the effect of some training data on the model. It's a lot cheaper than training from scratch because you already have the model. Each time unlearn is mostly a small cluster that you're trying to do. Okay. So unlearning is, of course, explored very well in kind of privacy domain. People try to unlearn this for right to be forgotten. So we took a look at some of the existing unlearning techniques, and unfortunately, they don't work really well for our setting. Right? This is because we don't really care about privacy guarantee in this case. All we care about is to just functionally remove the impact of this training cluster from the model. So as a result, we try to speed up the current unlearning techniques. We propose our own approach we call functional unlearning. Right, this is very straightforward. The idea is, we all see this graph. The training process is basically you start with, a random initialization. You slowly take gradient step to a local optimal, right, in this case. And then for functional unlearning, we simply try to revert this process, right? So we have a good model, local optimal, and we will slowly unlearn this model so that it will perform very poorly or has very high loss on the data you want to unlearn. Okay, so specifically we do this by training the model to output not the correct label for each of data we want to unlearn. We're going to output this uniform probability vector, right? So this vector is simply, a uniform probability across all output classes, right? That kind of equivalent to the model does not know which class this current input belong to. So you just output equal probability across all labels. So you just use simple gradient descent to optimize the model to output this vector on all the data you want to unlearn. And of course, at the same time, we retrain the model to make sure it doesn't impact the classification on the rest of the training data. Right, so this is the optimization function, the simple loss function gradient descent with respect to the uniform vector. So this basically makes the whole unlearning process into a simple fine-tuning, right? You just need to fine-tune a couple epoch. You will be able to observe the unlearning effect. And so this will reduce ImageNet forensics process from 1 month to around like 2 hours. All right, so this is how the entire forensic system works. Let's take a look at some evaluation results. Right, the evaluation is pretty straightforward. We take some existing data set, inject poison or backdoor inside. We test 4 types of backdoor attacks, as well as 5 types of classification tasks. And so what you do is the evaluation metric is this two, right? Is after the forensics, which will output a list or a set of poison data that they think contribute to a misclassification, we'll calculate the precision and the recall of the identified poison data when compared to the ground truth poisoning data. So this is some of the results, right? We can achieve very high recall as well as precision, 97% recall, and I think less than 0.9% false positive rate. Right, in the forensic setting, false positive rate is actually very important in the sense that you don't want to, mistakenly blame some people for injecting poison data when they didn't do that, right? So we can achieve pretty high precision in all these cases. We also took a look at clean label attack. Right, clean label is fairly different from backdoor attacks or Trojan attacks. Right, you rely on a fairly different attack method and intuition. But the same kind of traceback core intuition still holds, is that these poison data, after you remove these poison data, the attack is no longer successful, right? So the poison will cause the attack. So we try the same traceback system, and it actually works pretty well on existing or state-of-the-art clean label attacks. They can achieve very high precision, but the recall is a little bit lower. And we find the reason that recall is a little bit lower is because clean label attacks has more constraints or has a weaker attack strength compared to backdoor attack, right? That means some of the poison data are simply just not effective to contribute to this attack, right? That explains why the recall is much lower compared to some of the backdoor attacks. All right, so we of course also took a look at some countermeasures, is how can attacker to evade this forensic system to not get caught. And so we am not going to go into details the different countermeasures we discussed, but I think the idea is to circumvent the clustering step. Is how do you make sure the poison data to be sufficiently close to the benign data so that the clustering cannot separate them very well. Right? So we find that these attacks are not very successful at circumventing our defense, and the reason is there seems to be some fundamental constraint on kind of the separation between poison and benign data, and also the success of this attack. Right, that means sure you can move your poison data very close to benign data in the feature space, but doing so will significantly impact your poison attack success rate. Right, so these are kind of some results for the forensics. So before I move on to the second paper, is there any other questions about the first? Of course, we can talk about have Q&A in the end as well. All right, let's move forward. All right, so the second project we took a look at is completely different from the forensics, but also a different types of post-attack analysis for white box adversarial attacks. Okay, so this is a CCS paper that was a couple months ago. All right, so let's shift gear a little bit and talk about white box adversarial examples. Okay, so white box adversarial examples are, I think we all know, is just attacker gain full access to all the model parameters, architectures, as well as all the information about the defense and runtime parameters that you're using. And often viewed as very strong, right? I don't think there are very good solutions for defense to stop this white box adversarial attack today. And one question people have is, well, are these white box attacks even realistic, right? Like, what are the chances you gain access to all the, GPT-4 parameters? And what are the chances you get, the facial recognition screening model used by the airports, right? What are the chances you're getting all their parameters? But it actually can happen in the real world, right? Because server breach does happen, right? These models mostly run on cloud servers and sometimes even replicate across different nodes. So if part of your server has been breached through some traditional, server breach server attacks, it is possible for them to extract the exact model weights as well as any runtime defense that you put in place. Right, so server breach, of course, is not rare. We have, Uber, American Airlines all suffered from big major data breaches last year. And in most of cases, attackers have gained access to a big part of the infrastructure. So it's very likely that they indeed have gained access to some of the neural network models hosted on these servers. Okay. So these are the cases where white box attacks are indeed very possible to happen. Let's take a look at what happens afterwards, right? Let's say we are the US border control or the European border control. We have deployed face recognition models to verify traveler's identity, right? And we deploy this model. Of course, we train this model using a lot of proprietary data, deploy this model in the cloud, and at some point in the future, right, the server is breached by an attacker. And the attacker basically gains access to all the model weights as well as the defense that we put in place. So once model is breached, as we said, the white box adversarial example become very trivially to generate. Right, attacker can take off out of the shelf GitHub repos to produce adversarial attacks, and it's very hard for us to defend against this. Right, strong adaptive attacks can bypass most of the existing defenses in these cases. And one possibility is, well, what about retraining, right? What if we just throw away this model, change the model architecture, and retrain on our data set? Will this stop this attack, right? It is possible, but not guaranteed, because attack is very likely to transfer between two models that are trained on the same data set or similar data set. So it seems that the only option, or for these security critical situations, the only option after a server breach is really for service provider to stop using this service to retire the deployed deep neural network model, right? And once you retire this model, they'll induce a lot of cost, right? This is because all of your model are trained with tons of compute and time, and there are millions of dollars spent on training these models. But this is not most important, right? The most important is some of the data sets are very hard to collect. For example, I think there is a cancer genome data set that took 17 years to collect because there are only so many patients who gave consent to use their cancer genome imaging for this purpose. Right? So these data are just simply not reproducible. And so once your model has been leaked, the data set basically more or less go to waste. And still, this is still not the worst case, right? The worst case is there's many models today or many companies today overly rely on deep learning models so that they cannot even retire these models, right? For example, let's say Uber was recently breached. Uber cannot just say, well, let's not verify all the driver identities because our face recognition model was breached, right? Because that will be such a security problem. So what ends up happening in these cases is even after a breach, Uber will still keep their face recognition model running, but they know that there are attackers out there who have this model, can trivially generate white box adversarial example to bypass this type of verification. Right. So in our work, we took like this problem and said, well, how can we fix this, right? How can we potentially recover a deep learning service from a model breach? And we call this a breach recovery problem. So more specifically, the goal of post-breach recovery is to, first, we want to still maintain the benign performance of the deep learning service, but also at the same time, want to stop attacks that are generated using the breached model. Okay, so what we do is pretty simple, right? You can imagine after the model is breached, all you need to do is somehow generate a new model, right? This new model will still maintain a high performance of the deep learning service. But the problem here is that if you want to achieve a high benign performance, that means the new model will be pretty similar to the breached model, right? That means attack will still transfer from the breached model to this new model. So to stop or to achieve the second goal, what we do is we're going to generate attack detector, right? This attack detector's goal is to stop attack from transferring or detect any attacks that are generated using this breached model. Yeah, so this attack detector is a little bit different from the traditional adversarial attack detection problem that we have been working with. Right, so in this case, we only need to care about this breach model, right? We do not need to detect all possible adversarial attacks. All we need to do is to detect attacks that are generated using this breached model. All right, so before I jump into detail, let's take a look at the exact scenario of post-breach recovery. I say we have a deep learning service. We deploy, we train and deploy a model that's called the first model M1. At some time in some future time, right, the model was being breached and the attacker has gained access to exact model parameters. And shortly after the breach was detected, or the server breach was detected, so there are a lot of existing work kind of from system security, look at how do we detect server breach quickly. So we're not addressing that problem in our work. But after the breach has been detected, what we do is our recovery system will produce a new model M2 as well as a detector, right? And this detector's goal, as we said, is to detect any attacks generated on M1. So once we can do this, we can deploy M2 and detector and resume the service, right? Because we no longer need to worry about attack or white box adversarial attack generated from M1 since we have the detector, right? So this is how recovery works, but you may imagine there could be another server breach sometime further down the line, right? Your M2 and both your M2 and your detector is stolen, and the attacker can build adaptive attack to break both M2 and the detector. Right, so what we do here is we can recover for a second time, right? We can generate M3 as well as a detector that can detect attacks from both M1 and M2. And then we deploy M3 plus the detector to resume to recover from this attack, right? And now you can imagine this can keep going to support, the possibility of multiple server breaches. All right, so this is the scenario of post-breach recovery, but let's take a look at how this works. Okay, so the two questions remain. For first is, well, how do we detect these attacks? And the second is, how do we generate a new model? I'm going to talk about attack detection first. So we know that attacker has access to the breached model, right? We don't know exactly how they're generating adversarial attacks, but we know that they will somehow leverage the breached model. Right? It would be great if they don't leverage the breached model, then the server breach basically didn't happen, so it's not a white box attack. And so traditionally, or just intuitively, adversarial attacks are simply searching through the decision surface or log surface of M1 and find the local optimal where it costs misclassification but has very low changes to the image. Now, since this attack is optimized on M1, you will inevitably overfit on the specific loss surface of M1. Right? That means if we have a similar model, let's say M2, very similar decision surface, just slightly shifted, then this adversarial example will have much higher loss or much less optimal performance on M2 compared to M1, right? Because it's not optimized on M2, but only optimized on M1. And we can use this large loss difference for detection, right? Because for benign data, since they're not optimized on either of these models, most likely the loss of the benign data is very close, right? Because same benign data on two very similar models. So the detection is pretty straightforward, right? Each input coming in, we're simply going to calculate the loss difference of this input on M1 and M2. And if the loss difference is higher than a threshold, then we're going to flag this as adversarial attack. Right, so to know that attacker cannot calculate the loss difference itself, right? So cannot build an adaptive attack that directly minimizes the loss difference, right? This is because attacker only have M1 and you haven't breached the server twice, so it only has M1, does not have access to M2. All right, so this is how we perform detection, but now the question is, well, how do we produce M2, right? How do we introduce this small shift in the loss surface to produce this behavior? Right, we do this using something called hidden data, right? So traditionally or normally you train a model using its training data set. But for M2, what we're gonna do is we can add in some hidden data, right? We call it hidden data, but they're just simply some data points sampled from an unrelated data set, right? Say you're training CFAR, we sample a couple of data points from ImageNet data set. And the existence of this unrelated data set does not impact the benign classification because, well, they're unrelated. But the existence of them will actually change the loss surface slightly, right? The way they perceive images or the features will be slightly shift because of these hidden data. So we can produce a very similar model M2 to M1, but at the same time, they will have sufficient difference to observe the overfitting for detection. And the interesting part is attacker does not know exactly what hidden data was being used, right? You can imagine in a very high dimensional loss surface, there are many possible directions to move this loss surface, and randomly choosing some hidden data will just randomly choose a direction to move, but attacker cannot easily predict which direction was being moved. So building an adaptive attack will be very challenging because of this. All right, so this is how our system works. Let's look at some evaluation results. So before that, we need to introduce a new metric for this post-recovery problem, right? So for post-recovery, attacker does grow stronger as they breach a greater number of models. Right? As they get more information about how this recovery works, how the model works, they can construct stronger attacks. Right? More specifically, they can basically jointly optimize an adversarial attacks across all these models. Right? These attack will have much higher success rate because it doesn't overfit as much on each of the individual models. And we introduced a term called NBR, which is basically the maximum number of breaches that our recovery system can recover before the attacker has gained way too much information. So any future recovery is simply just not possible. Right, so we can achieve over, I think, 7 or 7 NBR against these data sets. I only show partial result here. There's more results in the paper, of course. So 7 NBR means if your server has been breached less than 7 times, then our recovery system can recover you. So you can still resume your service after having the recovery service to generate the detector and the new model. And of course, if your system has been breached more than 7 times, you probably have a bigger security problem than that, recovery and what we can handle here. Of course, we also look at some countermeasures. We show that it's very challenging for attackers to bypass this type of recovery or this type of detection. And the reason is that compared to kind of existing or normal white box detection, in this case, Defender actually has some information asymmetry, right? It has additional information about exactly what resources an attacker has. So all you need to do is to fingerprint or to detect whether attacks are generated using that resource. But on the other hand, attacker does not know exactly the shift of the new model, so attacking it will be very challenging. Right, so this is the second paper I would like to talk about. But just to summarize and also some takeaways, let's take a step back to look at the bigger problem. So I think hope I was able to convince you that the post-attack analysis is pretty valuable perspective for robustness. Right, beyond just simply trying to improve defense, we also need to address the cases where defenses fail, because it will in the real world. And how do you analyze, how do you use these evidence to analyze attack, right? And the additional information for the defender or for the model deployer will significantly benefit the security. And even take a bigger step back, I think many of my research has been focusing on is to kind of rethink the goal of adversarial robustness, right? If you take a look at deployed deep learning system today, the threat model they're under are fairly different from the threat models that we're considering today, or considering the literature. I'm going to give a couple of examples just to make this more concrete. So for example, I think most of our security research focused on, we have a model, we want to defend it from attacks, right? It's pretty single snapshot fixed model. But in real world, that's not the case, because companies keep fine-tuning their model every day on the new data coming in, or every month, and then keep evolving this model. So the threat model is actually pretty different, right? So the poison attack, whether it's poison attack, whether it's evasion attack or black box evasion attack, looks very different when your model is actually changing daily or changing weekly. And also because of this, I think we took a look at more existing literature, took a look at more kind of binary attack success or failure, right? Whether it's X% attack success rate, right? That's what we focus on. But realistically, there could be more stealthy attacks where, poison specifically, you can partially compromise the part of the model and slowly spread across the entire model over time, or can even spread across multiple models if there is some dependency across them. And lastly is what we talked today, right? We mostly focus on attack prevention in the literature, but there are a lot of broader measures, right? Attribution forensics are one of them. Of course, there is, measurement to understand exactly how real world attack looks like. And there are, of course, some work on that. So I think that's something we'll also be working on. Right. So I think, of course, we put all the papers online, as well as has a web page. The source code is also online, so welcome to check those out. And thanks all for listening. I'm happy to take any questions.